Good afternoon and welcome to the session. A little bit on my background. I've been coming to ACI since 1982 and began my career as a consulting engineer, working mostly in forensics. I had the privilege of working with two of the finest engineers in pre-stressed concrete, Morris Schupak and Mario Suarez. For the past 18 years, I've been with Preload, working exclusively with tanks. But in my prior consulting career, I was also involved with tanks and evaluating the performance of the tanks. Let's start the discussion here with our two sister documents that really provide sort of a feeder for the 350 spec and as well as for the 350 code. The first one on the left is the Guide to Design and Construction of Circular Wire and Strand-Wrapped Pre-Stressed Concrete Structures. This document is the fourth version of the document, and I chaired the effort to have this published last December. And also last November, the latest version of the AWWA D110 standard was published. And I believe this is the third or fourth revision of this document. The one on the right, the AWWA standard, is a mandatory language document, whereas the guide is not. Both cover construction aspects as well as design aspects. So we start with defining what we mean by a wrapped pre-stressing system. And it's basically taking high tensile strand or wire, pulling it before it's actually placed onto the wall. So all the stress is in the wire or the strand as the machines are riding around in a circle around the tank. These are examples of two different types of systems. The one on the left has a big spool of 270 KSI wire right there, and the machine is going to tension that wire and wrap it around the tank. That strand. This machine here is a wire wrapping machine. Basically, when we're dealing with wrap tanks, we have what's called a core wall, because the pre-stressing is exterior to the wall. It's placing this core wall in compression to counteract the pressures of the liquid. There's three types of wrapped core walls that our specification deals with. Well, actually, there's four, but these are the three common ones that are used in practice. Cast-in-place concrete with vertical pre-stressing tendons, shotcrete with steel diaphragm, and finally precast concrete with steel diaphragm. This slide illustrates the Type 1 construction. It's kind of we're dealing with Chapter 10 of the spec, but the internal tendons that are used to vertically pre-stress this wall in white there, those are white ducts. Those are covered in Chapter 9 that Steve just talked about. We have some features of this type of wall which are common to the other types, include the elastomeric bearing pads at the base of the wall, the PVC water stops at the base of the wall. Most of these tanks are designed with sliding base joint details that eliminate bending moments. The second type of wall that we deal with is a shotcrete wall with steel diaphragm. The diaphragm is used both as a form to shoot shotcrete against and as reinforcement of the wall. And this is the type of wall that we construct at my company. So my talk is going to primarily focus on this type of construction. It's the type where we precast these big wall panels in a horizontal bed and tilt them up into place to become part of the core wall. The definitions for diaphragm, it's not common to any other type of construction that I know of that's covered in ACI. It's not in the ACI definitions manual. It's thin sheet metal with vertical ribs that embed in the core wall of the tank. And as I mentioned, the first two functions are to act as a form and then reinforcement. And thirdly, it's an impervious membrane to liquid. So here we look at the field application of preparing diaphragm for a precasting bed. It's covered in our spec in section 10. There's an ASTM for this material. It's 26 gauge steel with fluted ribs. And they usually come in about 40-inch widths. So for the width of our panel, we'll take 3 of these sheets and seam them together to form a liquid-tight double-folded seam. The spec requires submittals that deal with the tank dimension and details, pre-stressing schedules, elastomeric materials, and also pre-stressed mill certificates. As design builders, the tank contractor would produce a full set of drawings with all the details. We are the engineer of record, but the consulting engineers are also involved in preparing the specifications for the project. And some of the structural details that they prefer would be on a set of owner's drawings. To start with the construction of the pad for the tank, most of these structures that I build are built on what's called 4-inch membrane floors. So our construction starts with a well-graded aggregate base. It's fine graded to a very tight tolerance. We choose a material here that has usually about a 3/4 inch material and down that's well graded, that can lock together so it can be compacted tight with a vibratory roller. Does not leave any kind of footprints from construction traffic, and it has to be put down with very tight tolerances because it's a thin membrane type structure, or membrane type floor system. When it comes to the floor construction, we sometimes separate the pipe encasements that come up through the floor from these thin membrane floors. So we'll have a thickened section around the pipes and cast a block around the pipes to allow the slabs to shorten unrestrained to eliminate potential for shrinkage cracking. Here's that block out that's going to block the concrete around the pipe so that we don't have a hard point. We have a thickened ring footing to take the vertical loads from the roof and from the wall, and then that transitions up into a thinner membrane slab that can deform with the shape of the soils that support it. Next, we move on to the construction of our primary water stop joint is between the floor and the wall. For the precast system, the water stop is placed with the floor, the wall is placed later, and a curb is added to tie the two elements together. So we have a continuous water stop, 360 degrees around, that's heat seamed and fused together, and also we spark test the water stop for any signs of leakage, because we don't want to have to deal with this after the tank is tested with full of water. The construction of the floor, we like to rigidly form a cantilever to hang the water stop so that we have very tight tolerances on the radial dimension of that water stop, where it is, because we have precast elements that have to come and line up on the outside of this. So it's critical to get the water stop in the right place. And it's nailed off on the top board of this form all the way around to keep it from moving, also tied to the rebar on the underside of the water stop. The membrane floor construction, we try to do this without joints. We like to avoid joints, and we can pour up to 250 feet without any joints. But to do that, we have to increase the reinforcement ratios substantially. For a 4-inch floor, that would translate to like number 5s at 8 inches on center to get to the 0.8% reinforcement ratio. The bars are supported bar supports with plates at 32 inches on center. Again, because it's a 4-inch floor, we don't want to have any deflections of these bars between support points. We want to have a very tight tolerance on both the depth of the bar and the cover to the bar. What we do to get the top cover is we lay out pipe screeds. In this case, these pipe screeds are about 1.25 inches in diameter, and we're going to be placing concrete and screeding to these pipe screeds to get the cover, and the very precise placement on the depth of the bars. Before we go into a major monolithic pour like this, we have to plan out for all contingencies. Sometimes we have 2 pumps because of the length of the boom. If we only have 1 pump, we have to have like a backup plan in case the pump breaks down. We often have another pump sitting over here in the wings. We also have backup concrete plants. If one plant goes down, we need to keep the joints fresh, and we need to keep the concrete flowing so we don't wind up with any cold joints. So here's a picture of 2 pumps working to place a pretty large diameter floor, and it's done in strips so that the concrete edge stays fresh throughout the construction. Curing is very important to prevent plastic cracking. We have such a wide pour on a wide open area. We have to be very careful about wind conditions and humidity. So we use fogging mists. We use curing compounds that are compatible, NSF approved, for potable water. And then finally, when the floor is ready, later in the day, it's flooded and left there for at least 7 days. Often we keep this wet throughout, or damp throughout the construction project. Moving on to the precast wall construction. This is a casting bed for the wall. The diaphragm has been laid flat on the bottom side. That's going to form the outside face of the wall, and it's reinforced vertically to take the bending moments from both the lifting stresses, which are often more than the temperature and moisture and pre-stressing bending stresses that the wall is going to see in service. So in the spec, we have to do this there are no cold joints in precast wall panels. They have to be poured in one continuous operation. Typically, it's almost like a precast plant quality in the construction. It's got a light broom finish, and every day they would cover it with polyethylene for curing. As far as the erection of the panels, these tolerances are not in our spec document yet. They're not in ACI 117 document for tolerance, but they are in those 2 sister documents which I mentioned, and as we progress on 350, you'll probably be seeing these types of numbers in the next version of the documents. So we have a vertical alignment between the panels, plumbness, how far the radius can be from the center of the tank. These precast panels have joints between them where the diaphragm is either overlapped or there'll be a cover plate that goes over on the outside, and there's certain sealants that are used and covered in our spec to provide a watertight seal here. The joints are filled with shotcrete. Some contractors use formed concrete to place this. Again, it's poured monolithically without construction joints. The other type of core wall, the shotcrete core wall, is built out in maximum 2-inch thick layers. Usually that would be limited to 1 inch at a time, applied as the shotcrete is hardening, and then they would increase it to 2 inches, and using shooting wires, which are high-strength wires or filament that are pulled under tension. Tension is in the spec. That gives them a guide as to how they're doing because you don't have a perspective standing this close to the tank to see how much thickness you're putting on. So this is all part of our spec requirement. As far as the other elements of shotcrete core wall construction, in the shotcrete wall, most often the diaphragm is closer to the inside face of the wall, and it requires 1-inch cover over the diaphragm. And then the concrete is built up on the outside face of the wall, and reinforcement is added as they work their way out. If they need bending on the outside face, they would add the reinforcement when they're constructing the core wall. So these are some of the types of equipment that have been developed to speed up the process and to and also for better quality control on building out core walls of shotcrete with automated equipment. The moist curing requirements are in 372. I believe they're also in the D110 document. And one of the reasons we don't have these requirements in our specification yet is that right now the appendices of the 350.06 code are sort of skeleton in nature, and in the next version of the code, those provisions are being brought into the code, and the spec is going to catch up with these types of requirements. The application of the pre-stress force is required to be at least the specified force and up to 5% over that. Here you see some openings in the wall. A standard pre-stress mill certificate for wire. It's a little bit different than strand, but the breaking strength is in pounds is here, but it's in the 226 KSI, 220 KSI plus tensile range. The minimum is 210, 215. Every foot of wire that's put on the wall will have a pre-stress measurement. This is a pre-stressing schedule. It shows the required force for every foot of height. It shows the force per the schedule, the minimum force that's required by the design, and the maximum force, which is that 5% value over the wall can take that, and it's all figured in the design. And every foot is, for wire anyway, there's an option to have an automated stress recording device for, I know the strand wrappers use a stress recording device. I have a machine for wire that also has a automatic stress recording device, but with wire, it's pretty easy to test the stress that you actually have in the wire using what's called a stressometer. And this is calibrated for each particular heat of wire that comes from the manufacturer that's going to be used on a job, is tested in the shop, and the device is calibrated to the actual wire. And it's within the pre-stress requirements are for the stress in the wire have to be within 7% of the specified. Otherwise, you stop the pre-stressing operation, and I don't think I've ever come across where we've had that kind of a range. The spec also has requirements for splicing wires that has to develop the full strength of the wire, and for the space between the wires so that you can get the shotcrete around the wires. And here is the spacers that were used to install that stressometer. In dealing with wall openings, the pre-stressing is brought out in layers above and below the opening. And when we get to the last layer of shotcrete, a wire that's going to go on, a steel frame would be installed, and the wire would be wrapped over that steel frame. And then after the shotcrete, it's clamped to pre-stressing wire clamps here. And after the shotcrete is fully bonded here, these wires will be cut, and the pipe that's going to go through this wall will be installed later. Moving on to dome construction, the critical aspects of dome false work are the strength design to carry these loads, and the geometry is very important. We have a series of towers here. We have rings that are going around. Each ring, as you get closer to the center of the tank, is rising to develop the spherical shape of the dome. Here you see these rings that are stepping up with the rise of the dome, and then there'll be ribs that will span from ledger to ledger. All of these towers and these heights of the ledger beams, the shape of these curved ribs are given, the construction dimensions are given to the 16th of an inch, and they're pretty well installed to good tolerances in the field. Here, the dome is ready for decking, and this is a dome that's been decked over. You can see the smooth spherical shape. In our design code, we have provisions for flat spots and limits on imperfections in the dome, but rarely, I've been with Preload for 18 years, and I've been on a lot of these domes. I've never come across an incident where I didn't see a nice smooth surface. The dome shells, like the membrane floors, are very thin elements. The domes are in compression. 3 inches thick is the minimum requirement for thin-shelled domes. So because we have a thin element, and we're very careful with bar supports. Here we have 24-inch maximum spacing on the shell reinforcement. On the edge, we're going to have a thickened edge to take any bending at the transition from the wall to the dome shell. We call this the fillet region. Here we've got, these are radial, and the bars that you saw before on the dome are each-way bars. And at some point up here, they'll intersect. But down here, we've got bar supports that are slab bolsters with runners with plastic tips. And we've got pipe screeds over the top of these to ensure that we're getting the right coverage. This is a 4-inch thick pour for the fillet. And we've got 1-inch bottom cover on the least bottom bar, and in this case, 1.25 inch cover on the topmost bar, and this is the pipe screed. So we have controlled casting between these screeds. Again, we're very careful with the amount of people that and the crews that we put up here that are experienced in casting domes on shapes like this uphill, and tight supervision to get the quality that we need for such thin elements. So external pre-stressed concrete tanks, to conclude my talk, have been around for a very long time. Preload has been around for 84 years. Some of our very earliest tanks were made with bar pre-stressing. This is the tank in Minneapolis. I believe it was featured in Concrete International last year. It's 82 years old in continuous service. It's not wire wrapped. It's got bar pre-stressing in it horizontally. But Preload was involved in the design of this tank for vertical post-tensioning with milder steel than the high-strength modern steel. This is a case of a 57-year-old tank up in New England, and it's really almost as good as when it was placed, and should continue to serve for a long time. So to conclude, we have in 350 these 3 documents, this one being a feeder document to the 2 mandatory documents, and this is the way that we build these tanks to last 100 years.